Hey folks, and welcome to section 9.3 lecture. We're now looking at what happens when you take an acid and a base and put them together to react. So we know what acids and bases are. They're both quite bad, right? Acids will donate protons, a bunch of extra H plus in your body, not good. Base will take protons away. A strong base will, take protons. Not good. However, right, think about what they're doing. So put them together. What do you get? Something bad plus something bad equals neutralization. Yes, when an acid and a base are combined, it's known as a neutralization reaction. And it, if presented in equal amounts, is completely harmless. Now, you might not want to drink it because it's actually going to produce salt water. You could drink it, wouldn't be very tasty. But the point is, it's neutralized. So that's kind of cool. We're going to look at specifically two types of neutralization reactions because there's kind of like two types of bases out there. Acids are all kind of the same. They all donate a proton. But the two types of bases, one are bases that have hydroxide, right? These are the strong bases, lithium hydroxide, magnesium, calcium hydroxide, things like that. And then also bases that have carbonates or bicarbonate within them. And the product here is a little bit different. And we'll go through both of these cases. Okay, so first, the case when we have hydroxide ion as the base, something like sodium hydroxide, right? So sodium hydroxide, NaOH, plus hydrochloric acid, HCl, forms water and salt, sodium chloride salt, and that's it. So this is cool, right? If equal numbers of moles of the base and the acid are combined, the result is a neutral solution. Of course, if equal numbers is the key here, right? Obviously, if you have more acid, right, you can only neutralize as much as you have a base there, to take up some of that acid. You'd have some left over. But if equal numbers, you end up with a completely neutral solution. And if we look at this reaction carefully, look, we've encountered this type of reaction before. It's actually pretty straightforward when you look at it. What type of reaction is this? See the question down here. Remember these from a previous chapter, right? Combination, decomposition, single replacement, double replacement, right? Well, which is it? It is double replacement, right? So take a look. We have the cation from one and the anion from the other join up, and then the anion and the cation from the other one join up, and so they swap. And in the swapping, you happen to get water and a harmless salt. But it's simply a double replacement reaction. Okay, so notice I put here the complete reaction or complete equation. But salt, when put in water, completely dissociates. A strong acid completely dissociates. A strong base completely dissociates. And so we actually can write the complete ionic equation, right? Because if you put sodium hydroxide in water, you no longer have sodium hydroxide. You have sodium ions and hydroxide ions. It dissolves. So if we split up everything that dissolves, we get this equation. Notice the arrow is here. Should have made that bolder. All right. And now it's kind of like a math equation. If something appears identical on both sides, it's not really part of the reaction. So notice Na plus is still Na plus, aqueous. Cl minus aqueous is still Cl minus aqueous. And so those are not actually part of the reaction. Those are what we call spectator ions, right? They are in solution, but they're not participating in the reaction. They're just spectators, right? So if we look at what's left over, if we take out the spectator ions and we look at what's left over, we get what we call the net ionic equation. And this is the true neutralization right here, right? Right. So if we just take out these pieces, right, we get hydroxide ion plus hydrogen ion makes neutral water. And you remember how in the past I've said H3O plus and H plus are kind of the same. If you were really particular about it, I'll just put it here where I have some space, right? We could write it like this. And then what would the product be? It would simply be 2 water, 2H2O. So it's often easier to just write it like this. But anyway, that's called the net ionic when you remove the spectator ions. And this applies to any hydroxide base, right? Lithium hydroxide would be the same, for example. So the core concept is that the reaction of an acid, any acid really, right? Doesn't matter which acid, and a hydroxide ion containing base produces water and a dissolved salt. The salt depends on which acids and bases you have. The net reaction is H plus OH minus makes water. And it's a neutral solution when equal numbers of moles of hydroxide and protons are combined. So I said any acid, and that's true, but there are some acids that are called polyprotic. And a polyprotic acid is one that has more than one H plus to give away, right? Protic, proton, poly, many, or more than one. So, for example, sulfuric acid, H2SO4, can give away 2 protons. Phosphoric acid, H3PO4, gives away 3. Citric acid gives away 3 as well. And so it will still neutralize exactly the same way, except we have to consider some balancing in this case, right? If you want to completely neutralize, say, sulfuric acid, well, you're going to need twice as much base, right? Because it gives away twice as many protons. So let's take a look at this. All acidic protons can be donated in a neutralization reaction. 1 hydroxide ion is needed to neutralize each acidic proton. The spectator ions combine in a ratio that forms a neutral salt. And so let's take a look. And of course, color coding, OH minus here is needed for each H, and there are 2 H's. So we're going to need 2 OH's, which comes from 2 sodium hydroxides and 1 sulfuric acid. And then if you were to go balance this thing, right, notice that you would end up with 2 waters, because we basically have OH minus plus H plus, and then we have another OH minus plus H plus. That makes 2 water. We have 2 sodium ions, 1 sulfate ion, and that gives us sodium sulfate, and that's Na2SO4. So the only really difference if you have a polyprotic is balancing at the end. Here, let's do some more practice with this. So I want us to write the complete balanced equation, and then the net ionic equation, and identify the spectator ions. So we can do the first one here. Calcium hydroxide So calcium is a +2 ion. So that would make CaOH2. Hydrobromic acid is HBr. I'm just going to write I'm not going to balance it yet. I'm just going to write the equation first. We always know that's going to make water and a salt. And the salt would be based on calcium and bromide. And knowing the charges on those, it would have to be CaBr2 aqueous. And now we want to balance. So notice we already have a 2 here for bromide because it's calcium bromide. So we're going to need 2 bromides, which also gives us 2 hydrogen to make 2 waters. And you can think of it different ways, right? We have 2 hydroxides, so we're going to need 2 H's to balance that out. Right, so there's the balanced complete equation. And if we remove spectator ions and only look at the net equation, that would be basically just the neutralization. We see that there are 2 OH minus 2 H plus, and it makes 2 water. And what are the spectator ions then? The spectator ions are calcium and bromide. Okay, number 2. We have LiOH and sulfuric acid, remember it's H2SO4. And I think, this is very similar to the one that just showed you on the last slide. So we have LiOH plus H2SO4. And we know we're going to get water, and we're going to get lithium sulfide. Lithium has a +1, sulfate has a -2. And to balance out, we need 2 lithium hydroxides, and we get 2 water. The net ionic is so. And the spectator ions are lithium and sulfate. Cool. All right, now notice the net ionic for these two are identical. Even though one of them had a monoprotic and one had a polyprotic, and then the bases had different numbers of hydroxides. In the end, it was the same net ionic. And just to clean things up for us, I wrote it all out here, and so we can see how that works out. All right, I'll end with one question. What is the correct equation for the neutralization of sulfuric acid again and KOH? Read through these carefully. There are a whole lot of different subtle changes here. And if you can read through this and solve this, you're doing pretty well for chemistry because, like I said, there's a lot of subtle differences and things to look at here. Make sure everything's balanced based on ion charges. Make sure everything's balanced based on the number of atoms on both sides. And yeah, I'll just be quiet and let you take a look and come back when you have an answer. Okay, welcome back. And indeed, the answer is E, right? Sulfuric acid. We were going to need 2 potassium hydroxides, get 2 water, and then the spectator salt is K2SO4. Okay, well that ends part 1. In part 2, we'll talk about carbonate ion-containing bases.